As we begin this chapter, we're going to talk about a concept called motional EMF. If you recall, in the last chapter, we talked about the magnetic force on a charge that was moving through a magnetic field. If the charge was moving in a direction that was perpendicular to the magnetic field, then there was a magnetic force on the charge. It also turned out that as long as there was a component of velocity that was perpendicular to the magnetic field, that magnetic force would exist. The force is just largest when V and B are perpendicular to each other. So as a reminder, phi is the angle between the velocity vector and the magnetic field vector. So if that angle is 90 degrees, then the force is largest because the sine of 90 gives us 1. All right, so motional EMF. If I have a magnetic field, so let's say we have a region here, big old region, that has a magnetic field. I'm going to just do a big X instead of a bunch of little X's. So let's say we have a magnetic field in this region that points into the screen. If I have a positive charge in this region moving to the right at a single moment in time, with the right-hand rule, so if I put my thumb in the direction of V, and then I put my index finger or pointer finger in the direction of B, so my thumb of my right hand, I'm pointing to my right, because that's the direction I've drawn the velocity in. Now I need to rotate my wrist so that I can point with my index finger into the screen. So thumb to the right, index finger pointing into the screen. Now if I hold my middle finger bent, my middle finger points upwards. And by up, I mean towards the top of the screen. That means there is a force on this charge, a magnetic force on the charge, which in turn causes this charge to move upwards. And as we talked before, the charge will end up moving in a circle, or at least a portion of the circle. If it leaves the magnetic field, it won't continue the circle. But if it stays in the magnetic field, it will result in circular motion. Okay, with motional EMF, we're talking about a conductor. So let me draw a different picture here. So still having a magnetic field that points into the screen. But now, if I have a conductor, not a magnetic conductor, so something like aluminum is not ferromagnetic, copper is not ferromagnetic. We don't want it to be ferromagnetic because if it's ferromagnetic, that the magnetic domains will just line up with this external field, and then the conductor will just be attracted to whatever's creating the magnet. So we do not want this to be ferromagnetic. If we get this conductor moving to the right, the conductor is made up, of course, of a bunch of charges. There's protons in the nucleus of the atoms. There's electrons in all these atoms. So as this conductor moves to the right, if we think up to this top situation where a positive charge experiences a force towards the top, well, that means a negative charge in the same region would feel or experience a magnetic force downwards. And so its motion would be down. So in this conductor, because the conductor easily shares its valence electrons, there's a magnetic force that pushes electrons towards the bottom of the conductor. And that in turn leaves the other end of the conductor with a net positive charge, because some of those electrons have moved to the bottom. So the motion of the conductor in the magnetic field, so this magnetic field is created by something else. The motion of this conductor in the magnetic field causes a separation of charge. And it's specifically because of this motion, and the motion being perpendicular to the magnetic field. There's force, magnetic force on these charges. Well, if we have a separation of charge, that's similar to what we were talking about with a capacitor or a battery. When we have a separation of charge, there is an electric potential difference. A voltage difference, a delta V. This is what we're calling the motional EMF. EMF, recall, is the term we used, electromotive force. We've used it mainly to talk about an ideal battery, but we still mean potential difference. Here we're calling it motional EMF because the only reason it exists is because of the motion of this conductor through the magnetic field. If the conductor stopped, moving, this motional EMF would go away, meaning the electrons would move back, because if it stopped, there's no magnetic force on the electrons, and so they would move back and balance out and make the whole conductor neutral in every spot again. So the whole reason we get this separation of charge is because of the motion. And hence, that's why we call it motional EMF. Now, in our conductor, as it continues moving, with this separation of charge, we actually end up with an electric field in here. If you recall from previous chapters, that was supposed to be electric field, not force. Sorry. We get what is called an induced electric field. If you recall, potential difference and electric field always go hand in hand. Electric field always points from high potential to low, so from positive charges to negative. With this electric field, we call it induced because it is occurring because of this motion. The electric field is not there because of some traditional battery, a voltage source like a battery, or a wall outlet. There's nothing else creating it, just the motion of this conductor through the magnetic field. So this induced electric field, now if we imagine I have this electric field, if I have an electron in an electric field, an electron is going to feel or experience an electric force that is attracting it to the positive charges. So there's an electric force opposite that electric field. What ends up happening is if that conductor continues moving through the magnetic field, the electrons, as we already drew in the original picture up here, these electrons end up experiencing a magnetic force towards the bottom of this region, so the bottom of the conductor. But then because there's this induced electric field, there's also an electric force towards the top of the conductor. And these two end up balancing out. So this electric force upwards balances out with the magnetic force downwards. In earlier chapters, we related the electric force to the electric field. So Q times E. Our magnetic force is QVB, and technically sine of phi, but our angle in this situation is 90 degrees. Our velocity is to the right. The magnetic field is into the screen, so the angle between those two is 90 degrees. So sine of 90 is 1. QE is equal to QVB. The Q's cancel. It turns out the induced electric field in the conductor depends upon the speed at which the conductor is moving and then the strength of the magnetic field. I don't know why that won't go down. Sorry. Okay, so the strength of the magnetic field the conductor is moving through. Now, if we want to relate this to potential difference, though, and not just the electric field, I'm going to slide this up a little bit. When we have an electric field, so just drawing the electric field we end up with in this conductor, electric field is related to potential difference, delta V. So not change in speed, change in voltage. Delta V and electric field are related. If you recall, delta V is the negative integral of E dot ds. To relate these two, this electric field is more or less constant throughout that conductor. So we can say that the magnitude of this potential difference is approximately the electric field times, so if we think negative E dot d, delta S. Delta S is the distance we move with the electric field. So delta S is the distance that these electrons end up separated by. In our book, as well as in our test notes, we call this just the length of the conductor. If I come up to the picture with my conductor in the magnetic field, this length, L, it's how far apart those charges get separated by. So E times L is what we end up with. That means the electric field is essentially the potential difference divided by the length of that conductor within the magnetic field. So how far apart the charges get separated on that conductor. If we plug this in for E right here, the potential difference divided by the length of the conductor is speed times strength of the magnetic field. So the potential difference that will exist across this conductor while it is moving depends upon how fast the conductor is moving, so the speed of the conductor itself, the strength of the magnetic field the conductor is moving through, and the length or width of the conductor within the magnetic field. Now, this is just the magnitude. You will see this when we talk about it in terms of motional and call it EMF. Instead of writing delta V for potential difference, we use the EMF symbol again, which we used before for our ideal batteries. Now, this can be a little challenging to visualize, so I found a little video clip on YouTube. I love YouTube. So in this video clip, you're going to see, well, let me get it started. Okay, so I'm pausing this really quick. So the U-shape, kind of gray, dark gray, is our magnet when we see the rectangle underneath. Whoever's hands we're seeing is holding a conducting rod, and he's going to take it along a couple other metal rods, all of these being non-ferromagnetic. So the magnet itself, of course, is a magnet, but the other rods are not ferromagnetic, meaning they're not attracted to the magnets. He's hooked up these rods that are horizontal to our galvanometer in the back. It's measuring current. So when the rod that the person's holding onto moves, watch the galvanometer. It's essentially a multimeter is what it is. So there is a reading on this meter when that rod is moved. Whether the rod is moved to the right or the left changes how the reading on that meter goes as well. So just playing that portion again. Okay, so the reading goes back to 0, meaning no current when the rod is not moving. And then it reads left or right, meaning current flowing one direction versus another, based off of the direction the conductor was moving. So if we were to draw kind of a diagram representing what we just saw, we still had a region where there was a magnetic field. I don't know whether that magnetic field pointed from the top magnet down to the bottom or vice versa. So if I was able to look down on this setup, and he has this rod that he moves, he or she or they, I actually don't know the person, obviously, I only see hands, that rod was in contact with these other rods that were already stationary. And I realize I'm actually drawing the magnetic field larger. So these ends of these rods on the left side were connected to the meter and could read the current flowing through the meter. The reason there can be current flow is because of the conducting contact between this rod that is moved and then the other horizontal rods that are there. So there's a complete path or circuit for charges to move through. Whether the current went left or right, or I guess clockwise or counterclockwise. So this one, A versus B, it went one way or the other, was dependent upon how the conductor was moved. So as this conductor was moved through the magnetic field, so there was a push. The person had to physically push this rod through the magnetic field. If the magnetic field in this region was from top to bottom, so this is as if I'm looking at the setup from above. If the magnetic field was from top to bottom, so that I saw the magnetic field, if I could, pointing away from me, if I imagine just a little electron in here, a single electron in this conductor moving to the right, if I think about the magnetic force, the right-hand rule, the V cross B, would give me a force that was up in my picture, meaning towards the top of the rod. But that is just V cross B, meaning positive charges would be towards the top. So positive charges would get pushed towards the top part of the rod, negative charges would be pushed towards the bottom part of the rod. So externally to the rod, we would have current coming this way from positive. It would continue through the meter towards negative. We call this an induced current. And it's just based off of how the charges would get separated in that conductor. The current would continue through the conductor from negative to positive, and it would make a complete loop because of this conducting path. When the person pulled the rod back towards this left side, so after it had gotten pushed all the way to the right and pulled it back, the current flowed the opposite direction because of this opposite velocity direction. If the velocity is opposite in the same magnetic field, the charge separation is opposite what it was. So by induced current, we mean we're getting this current flow without some sort of traditional power source. There's no battery. There's no wall outlet. There's nothing attached to the system to put electrical energy into the system. That electrical energy and thus current is coming because of a mechanical push. The person is actually pushing or pulling on this conductor. Okay. And it turns out you can't just give the conductor a quick push. Well, you can, but it won't keep going on its own, is what I mean. If you want this induced current to continually be induced, you have to continually keep pushing. Okay? So motional EMF is a voltage difference, a potential difference because of motion of a conductor through a magnetic field. And that motion needs to be perpendicular to the magnetic field for this EMF to be induced. So ultimately, we're getting an electric field because of the separation of charges, which in turn means potential difference. If there is a complete path for charges to move through with that potential difference, then that will also result in induced current. So we're going to be looking at this concept throughout this chapter. The general concept in here is called induction. We're getting voltages, potential differences, and or current because of somehow motion through the magnetic field. We're going to see it's also related to just changing a magnetic field. So we get something, current, voltage, that we wouldn't normally expect. Now, it's not getting it from nothing. We have to put energy in to make this happen. So we're going to talk about it in another way as well, not just the force on the charges, but in terms of magnetic flux. So the next concept we'll talk about is magnetic flux.